So the next homework assignment, the focus is going to be on sketching the graphs of derivatives given an initial function. But before we dive into just sketching derivatives of functions, we first want to discuss when a derivative doesn't exist. What are the conditions under which the derivative doesn't exist? So in the previous set of videos, we found the derivative by using the difference quotient and taking the limit as h goes to 0 on the difference quotient to find the slope of the tangent lines to a graph. And we named the function that described the slope of the tangent lines the derivative. And we use this notation to denote the derivative. One of the key pieces of the definition of the derivative, though, is that the function for which you are applying the difference quotient has to be continuous on the interval over which you're taking the derivative. So the first place for which a derivative of a function isn't going to exist is at discontinuities, because by definition, a derivative can only be taken over an interval for which the function's continuous. So here there's a jump discontinuity. You can see at x equals 1, the graph is jumping up from here to here. So at this discontinuity, the derivative won't exist. The derivative exists on either side of the discontinuity. So just because the derivative doesn't exist at the discontinuity, which is here, doesn't mean the derivative of the function doesn't exist. So if we call this function f of x, f prime, the derivative of x, f of x, does exist. But the derivative doesn't exist at 1. F prime of 1 does not exist, even though the derivative is going to exist everywhere else. So here's another discontinuity. This is a removable discontinuity. The graph looks to be linear everywhere except at x equal to 2. So at x equal 2, the derivative will not exist. It will exist on the left side of that discontinuity. The derivative exists on the right side of the discontinuity. The derivative doesn't exist at the discontinuity. Here the discontinuity is a vertical asymptote. So this function, let's call him g of x, g prime of x does exist, but not at the discontinuity, but not at x equals whatever this discontinuity value is. X equals a, where a is the location of the vertical asymptote. So at the vertical asymptote, there's no derivative, even though the derivative exists everywhere else. So discontinuities. The derivative doesn't exist at the value of x, or at the input value that's causing the discontinuity, although it's probably going to exist everywhere else. So the next way a derivative can fail to exist is if the tangent line, so here's a graph right here in blue, we'll call him f of x. And at this point on f of x, notice that the tangent line is vertical. And the slope of a vertical line doesn't exist. Slope of vertical line does not exist. In fact, the slope of a vertical line, there's a sense in which we can say the slope is infinite. So if the tangent line to a graph, because remember the derivative gives you the slopes of the tangent lines for a graph, but if the graph has a vertical tangent line, the derivative won't exist at that point. So think about it this way. The slope of a line, we calculate that by taking delta y over delta x. And the derivative, to get the derivative, the slope of the tangent lines, we simply are taking the limit as the delta x goes to 0 of that ratio delta y over delta x. So you're calculating the slope of a line. Well, if you have a vertical line, let's say this is 2 over 1 up. So here's the point 2, 1, and let's say this is the point on the line 2, 2. Well, if you try to calculate the slope of this vertical tangent line, what's going to happen? Well, you'll get change in y, which is 2 minus 1, divided by change in x, which is going to give you 2 minus 2. You wind up with 1 over 0. But division by 0 is undefined, and you can't do that. You can't put a 0 in the denominator. So the slope m of a vertical line doesn't exist. So anytime you have a graph and there's a place on that graph where the tangent line is vertical, the derivative won't exist at the value of x at which the vertical tangent line exists. It'll exist everywhere else, but not where the tangent line's vertical. So the other way you can fail to exist is at cusp. So cusp in a graph are just these sharp changes in direction graphically. And when you have a cusp, the derivative doesn't exist at the value of x at which the cusp exists. So this graph right here, the derivative exists except at the sharp corners. And graphically, you can kind of think about what's going on. So if we pop GeoGebra Classic open for a second and take a look at it. So here's the graph that we were looking at on the previous slide. And here's the cusp. So remember, the derivative is just the slopes of the tangent lines to a graph. So at this point right here on this graph, I have drawn in the tangent line. And think about what happens as this point on the graph moves closer and closer to the cusp. At each place, you have a tangent line. The slope of that line is the derivative of the function. And right now, notice that the slope of this line is going to be negative because the line's going downhill as you move from left to right. Well, when you get to the cusp and you switch over to the other side, notice that suddenly the tangent lines have positive values. So at the cusp, the tangents, the slope of the tangents are switching quickly from negative to positive. There's a disagreement on either side of the cusp regarding what the tangent line value should be. So at that cusp, you don't have a derivative. That quick switch from negative to positive on the tangent lines, if you think about it graphically, it's going to cause the derivative not to exist. Here, as I get close to this cusp, again, I get that quick switching in the slope of the tangent line. So at that cusp, there's not going to be a derivative. So those are really the three big ways a derivative is going to fail to exist for us. At discontinuities, there's no derivative. Vertical tangent lines, there's no derivative. And at sharp graphical cusp, there will be no derivative.